Hi, everybody. Thanks for coming back. Yeah, so let me start simply by recalling a little bit what I did last week, so that I mean, the whole lectures are about SL2 at admissible level. And so I started last week by telling you that I think affine vertex algebras associated to Lie algebras are central, because every vertex algebra that we know somehow comes from an affine vertex algebra. And then I explained to you how I think about representation theory. What are the three cornerstones of what you want to do? So the first thing is, if you want to do representation theory of a vertex algebra, you want to classify. You want to understand your your category of modules of interest as an abelian category. And then once you have this, you also want to understand monoidal structure. And the key issue there is, in the very first place, the existence of the tensor category structure. And then as a final thing, you also want to study it. And I then last Tuesday, so the last two lectures, I already focused mostly on SL2. I told you the challenges that appear and where we stand. And and in particular, I tried to, I mean, I sketched a theorem that will appear soon, it's as good as done, work with Arakawa and Kawasetsu, where we get a complete classification, a complete characterization of the abelian category of an affine vertex algebra of SL2 at admissible level. And so let me recall this all a little bit.
Thomas,
yeah.
Sorry
Yes.
to interrupt, but we cannot see your screen yet.
Oh, these are all. That's of course not. Well, I didn't show anything yet, so thanks for noticing. This would have been so. The review. We are interested. Thanks, Flora. Interested in a suitable category of modules of an affine vertex algebra. So here, LKG stands for the simple affine vertex algebra of G at level K. Here, G is simple Lie algebra. Eventually, you would also like to look at super algebras. And it turns out the best level to look at for the moment, at least, are admissible levels for G. Okay, and now what I presented last time in the very first place, I gave you 4 categories that I claimed are interesting. A big category that has as few conditions as possible, and then smaller categories that are better known. So this big category is called the category of weight modules. And it has, what is this? The objects are finitely generated. Smooth is the condition that there are modules for the affine vertex algebra, for the universal one. And then weight is the condition that the Cartan subalgebra acts semi-simply. And bigraded weight space is bigraded by a generalized conformal weight, and Cartan subalgebra need to be finite dimensional. And then, of course, we also want them that they are modules for the simple quotient. Now, this category has a few features that one might claim to be unusual. Namely, what are usual VOA categories that you look at? Usually, you're looking at lower bounded modules. They have a top level, a level of a subspace of a lowest conformal weight, and this is this doesn't hold for the usual module. So modules are usually not lower bounded, and but of course we have an interesting subcategory of lower bounded modules that is useful in many respects, but the general modules are not lower bounded. And also, if you just look at conformal weight spaces, they are not necessarily finite dimensional. Okay, and so these are two features that make it maybe hard, not maybe, surely hard to study. But then I presented some techniques how to study them last time. And so in particular, what we had is we had this hierarchy of categories. We had the very small category where conformal weight spaces are in fact finite dimensional. Then we had an intermediate one, which is the category O, which in fact is not that important for these discussions. And then in the middle, we had the category of lower bounded modules, and then this category of weight modules. I often also just said it's the big categories, our biggest category. And now the story is that one important result was that, so first of all, simple modules, lower bounded simple modules can be classified. Kawasetsu and Redoubt that. But then it turns out every simple module is related to a simple lower bounded module via the spectral flow automorphisms. So this means classification of simple modules is not a problem anymore. So what you have to understand is what are possible extensions. And I told you, I sketched you criteria for vanishing of extensions. One very and we had this picture that I drew, which is this kind of picture one has to have in mind for that. So often extensions simply have to vanish because any map from one module to the other one has to factor through an empty space, so it can't exist. And then the other useful criterion we got is that extensions on just inside the category of lower bounded modules are completely characterized by its top level. So that means it's a problem of the finite dimension D algebra. And with all this, together with this very nice Adamovich trick, which allows to construct interesting extensions, one simply gets a lot of data that the category satisfies, and then it's an exercise in homological algebra, just playing with long exact sequences in cohomology to prove that the established properties already characterize the category uniquely. So it's and I think this is the good strategy, to simply find what you can find and then think about it carefully to hopefully see that you got everything. So, and let me now write this final result down as a theorem, which in fact I didn't do last lecture. Well, I did it in one form. I will write it down again in a different form. So, and for this I introduced an auxiliary category called the atypical category. And so it's the category which with a set of simple objects parametrized by the integers. So we call them Ln. And these simple objects, they have projective covers Pn, and they are best described. They are also injective hulls, and they have the Löwy diagram of this type. So this reads as, this means this projective cover of the simple module Ln has the simple module Ln as submodule. It has 3 more composition factors, so 4 composition factors together. If you quotient by the simple module, then that quotient has Ln minus 1 and plus Ln plus 1, these two modules as semi-simple submodule. If you quotient again, you get Ln back. So it has this Löwy diagram, and then by the typical category, we just mean vect. So the semi-simple category with a single simple object. And then let me introduce some notation to formulate the theorem precisely. So for this, I introduce 2 sets. I is just the set of tuples R and S, where R is an integer between 1 and u minus 1, and S is an integer between 1 and v minus 1, and that J be I modulo the relation that Rs is related to u minus R, v minus S, and of course itself. So then the theorem is the following. So this is this theorem we've been looking. This is the theorem we really wanted to have. So let a k be an admissible level for SL2, so we can write it as minus 2 plus u over v. So this is where these 2 integers u and v come from. So u and v are co-prime positive integers, in fact, at least equal to 2, both. So then as abelian categories, one has the following equivalence. The category of weight modules of SL2 at this admissible level decomposes into blocks. It's a huge sum of typical blocks. So here this R and S are you can think about it as Casimir eigenvalues. L is the spectral flow label, and then here we also need a weight label. And remember that these lambda RS and U minus R, V minus S are simply specific weights. So it's not that important anymore at the moment what they are exactly are. So we get this huge sum of atypical blocks, and then we get a small sum parameterized by the set I of atypical blocks. Right. So what does this mean? Is this category of weight module is huge, right? You see all the what it's parameterized, but it's generically semi-simple. Almost every simple object is of the typical type, but then it has this finite number of atypical blocks. These interesting blocks that are of this type, each block having this infinite number of simple modules, and each simple module allowing for an extension of this small diamond type, this thing. So this is kind of nice. It gives a complete classification, right? It's the understanding of SL2 at admissible level as an abelian category. And now, well, now we of course want to go on. So this is maybe finishes the review part of today. And where do I want to go? Well, I next want to discuss tensor categories. But before I do so, I thought I'll do a small excursion to quantum groups. So if you ask somebody who is simply interested in having braided tensor categories, then that person wants to have a source that that gives you such categories, and it's kind of well known that there are two good available sources, namely categories of modules of a vertex algebras and categories of modules of a quantum group, or more generally a Hopf algebra or quasi-Hopf algebra better. There's a big difference between the two. Well, quantum groups are very nice and explicit, right? They're described by generators and relations. Representations are finite dimensional and explicitly describable. The tensor structure is, the tensor product is explicitly given by a co-multiplication. R matrix describes braiding, etc. It's all very explicit. So this means the quantum groups are in many respects much more pleasant. And but a general theme is you expect that that there's always a nice relation, that it's categories of VOAs and categories of quantum groups, they share a lot of similarity. So the very famous example is the work of Kashtan and Lustig in the 90s, who showed that for generic level, just the category of ordinary module, this very small category that I denoted by Kashtan and Lustig, of an affine vertex algebra and the quantum group at corresponding root of unity are equivalent as braided tensor categories. So that they are equivalent as abelian categories is trivial, but they are actually equivalent as braided tensor category. That's highly, well, yeah, highly non-trivial result. Anyway, it turns out the quantum groups that seem to tell us most about affine VOAs at admissible level are small unrolled quantum group. So this is a small u to indicate that it's small. The upper index h indicates that it's unrolled, and let me define it, that you have seen it. So it turns out that this unrolling procedure has the effect that that you have a huge category that has uncountably infinitely many blocks, but the generic block is semi-simple. So a similar behavior as we now also observed for SL2 at admissible level. So we fix Q to be an even root of unity. So 2R root of unity. I just do this because that's the one relevant for the correspondence. And so this quantum group is generated as an algebra by EF, K inverse, and H, subject to a bunch of relations. So the symbol inverse, of course, wants to indicate that K inverse times K is always acts as the identity on anything. Then you and then if you conjugate E with K, then that is the same as multiplying E with Q squared. Similar for F, just that you have a Q to the -2. And then the commutator of E and F is given by this expression, Q minus Q inverse divided by Q minus Q inverse. And then you have, and with this is essentially just the usual quantum group, the relations. But now you have this additional generator H. So H you want to commute with K. And you want H wants to be the H of SL2 in many respects. So H has commutation relations with E to E, very much like in the SL2 case. But now the only difference is here the commutator of E and F doesn't give you H, it gives you K minus K inverse. So and now what additional relations do you require? You want this to be restricted, so you also require that E and F are nilpotent, that their rth power, so remember Q is a 2rth root of unity, the rth power of E and F vanishes. So this is the algebra structure of this unrolled quantum group. It also has a co-algebra structure. That's of course very important because it tells us how the algebra acts on tensor products. So co-multiplication of E is not trivial. It's 1 times E plus E times K. And similarly for F. And these are the usual co-multiplication formula for quantum groups. I just thought I repeat it because I think it's very good to have seen these unrolled quantum groups. They are much less familiar than the usual quantum groups, but I think they play quite an important role. And H, this additional element, you just give it trivial co-multiplication. Okay, and then in order to make it to a Hopf algebra, you also need a co-unit. So it's just very quickly, epsilon, the co-unit, maps everything to 0 except k to 1. And then the antipode is of this form. So really it is very similar like the usual quantum group. The restriction comes from the requirement that E and F are nilpotent here, rth power vanishes. And the most important thing is that one introduced here this additional generator H. And now H wants to be a logarithm of K. And this but this doesn't appear in the definition of the quantum group. It appears only in the definition of a module, just because you eventually might also like to have more general types of modules. But you call a weight module a module of this small unrolled quantum group. And what do we want? First of all, we want the usual weight condition. This means we want Cartan subalgebra to act semi-simply. So here, this H plays the role of that. Acts semi-simply. And we want H to act like a logarithm of K. This means we want this relation as operators on V. So in particular, what it means is you can have modules that are isomorphic as modules for the usual quantum group, but you can have, but the action of H differs by a phase, so that Q to the H and K still coincide, right? So you have a much bigger room for modules. And also note that for the usual restricted quantum group, you require that K to some power, K to the 2R, to act as the identity. Here you don't require that. And that again, that also gives you a lot of freedom for more modules. Anyway, there's a very nice paper which I can recommend reading. It's called Remarks on the Unrolled Quantum Group of SL2 by Constantino, Gia, and Patiro-Miron. And there they classify the category, weight modules of this unrolled quantum group, which is really not a hard problem. And it turns out the classification is as follows. You have here a huge set. What it is not precise, not that important, but you have for the generic weight label, a Verma module will be simple and projective and injective, so it will just give rise to a trivial block, a block with a single simple object that is semi-simple. And then you will also have a finite sum of atypical blocks. So this means in this example, one observes that while the carriers of weight modules of SL2 and of the affine VOA at admissible level are not equivalent as abelian carriers, they are blockwise equivalents in the sense that both of them admit only two types of blocks, the trivial block, the typical block, and this atypical block, and those only appear. Now, we strongly believe that this is not a coincidence, but that in general it should hold that the category of weight modules of an affine vertex algebra at admissible level is shares some.
Hi, Thomas, may I interrupt you for question? So here, what's the coefficient of z? TZ?
It's an R. It's the R. You mean this
R?
R, right?
It's
Yeah.
R, right?
R and
the second term, I from 0 to R. Yeah. Okay. Yeah. Okay. Yeah. Mm-hmm. Thank you.
Yeah, you're welcome. So in general, what should happen is that you have more types of blocks. You not only have a very atypical block and a typical block, but you also will have somehow blocks in between. But you still believe that a similar correspondence should hold, but it should in fact be, and that has to do with the nature of these unrolled quantum groups, that the category dual to the, that it shares such a correspondence to the affine VOA should be a category of an unrolled quantum group for the Langlands dual Lie algebra. What you can see in one way, because really extensions go into spectral flow directions. Spectral flow is parameterized by co-weights, not weight. So that means somehow possible extensions are parameterized by co-weights that are small enough in a certain sense. Anyway, it seems this might be a nice guiding principle, and it turns out that so Matt Rupert, David Rideout, and I, we have a paper where we have done such a comparison between unrolled quantum group and SL3 at a special admissible level very explicitly, so that matched in fact really nicely. And there you already have many different, 3 different types of blocks. Anyway, what I want to say here is that we found a certain type of category, and this category was already known for this type of category for unrolled quantum groups, and that should definitely be a guiding principle for the future. Okay, now let's go on. Now I would like to talk about tensor categories. Now I can't talk about tensor categories directly. Why? Because the only good theorems that tell us we have a tensor category for a VOA are the original theorem by E.G. Wang, who tells us that we need C2 cofiniteness of a VOA to get a good vertex tensor category. And then Jinwei Yang and I, we observed that was a little bit, that was too harsh, and that you could weaken it quite a bit, but you definitely have to, you have to require that modules are C1 cofinite, and you have to require that your categories of finite length. Let me scroll a little bit back to show you the statement that I wrote down at some point. Right here we had this. So so C is the category of modules of a vertex algebra, and if it has this 6 properties, that every object is in this category C1 cofinite, it's an abelian category. Every object is of finite length, it's closed under contragradient and closed under tensor product, then we get a vertex tensor category. Now for this SL2 admissible level, our category of weight modules is abelian, finite length, and closed under contragradient. There is no problem. But it's whether it's closed under tensor product or not, we don't know. And it's totally not C1 cofinite. So still, I want to apply this theorem. I want to prove that SL2 has a vertex tensor category using this theorem. So how can I do this? And this means I have to do quite a bit of an excursion to tell you how I can do that, because it can't be very direct. And this excursion is called dualities, which is a really nice subject in its own right. So it's so I will tell you, I think I will give you an interesting theorem, but the way we achieve it is very instructive. Okay, and so dualities refers to isomorphisms between VOAs that you might naively maybe not expect, or let's say to interesting isomorphisms between VOAs. And here, the one that we are interested here is the let me call it S with a superscript C. So what it is the n=2 superconformal algebra. And maybe before I start, I'm sure most of you have heard about the W algebras. For example, the W algebra of SL2 is the Virasoro algebra. And more precisely, the Virasoro algebra at a central charge at this central charge, you get to this via quantum Hamiltonian reduction from the affine vertex algebra of SL2 at level K. Now, what do you see here? This formula is symmetric under replacing K plus 2 by its inverse. Right? So what it means is, in particular, the quantum Hamiltonian reduction of SL2 at level K and at dual level L, where K and L are related by the relation that K plus 2 times L plus 2 is equal to 1. Right? Write it in a nice and symmetric form. It gives the same W algebra, the Virasoro algebra. More generally, one has the statement of for principal W algebras, you have Feigen-Frenkel duality, which means if your levels satisfy a similar relation as this one, then the principal W algebra of G at level K and the principal W algebra of the Langlands dual of G at level L are isomorphic. And now, and for a very long time, this has been the only duality of W algebras that has been known. And then 6-7 years ago, Gayotto and Rabchak, they had a very nice physics picture of which I will not talk about here, but the point is that the dualities of the quantum field theories implied on a physics level that there are certain isomorphisms of associated vertex algebras, and the upshot of that was that there are then, you expect many more dualities between W algebras and super algebras. And the one I'm presenting now here is the simplest one of this new type. It relates the n=2 superconformal algebra at a central charge C to the affine vertex algebra of SL2 at level K. And anyway, long excursion here. So this algebra is strongly generated by 4 fields, 2 even and 2 odd ones. So I call them the even ones J and L. J is a Heisenberg field. So that means it has a second order pole. The norm is given by the central charge. It acts on the odd fields by ±1, hence the superscript. these odd fields have trivial OPE with themselves, and but the G plus with G minus is the most interesting one, surely. And it's of this form. And quite similar. So J prime denotes the derivative of J. And then L is a Virasoro field of given central charge. And is J and G plus minus are Virasoro primaries. Of conformal weight 1 and the odd ones of conformal weight 3/2. So this is one of the best known super VOAs. It's the physicists liked it a lot because this algebra you need if you want to look at supersymmetric strings. So that's where they maybe first came about. Okay, now the discovering the SL2 to super Virasoro duality is not that hard because what do you have? You have SL2 that's generated by your E, F, and H. Now so you already have a Cartan subalgebra, I mean a Heisenberg field, the H, and now you have your E and F. Well, they are not odd, they are even, and they don't have conformal weight 3/2, they have conformal weight 1. So what can you do? Well, maybe I just take two odd fields of conformal weight 1/2 and take, let's call them B and C, and take the the product of E with one of these fermions and F with the other one of these fermions. And indeed, if you do this and just call these two fields G plus minus, compute their OPEs, you will observe, that's of course a longer exercise, that they obey the OPE relations of the n equals 2 super Virasoro algebra. So this means meaning you have a homomorphism from your super Virasoro algebra inside the affine vertex algebra of SL2 if you add two free fermions. Here, so here by B and C, I mean, what's that? Here by B and C, I mean the super VOA of two free fermions. So here they are fermions, meaning they are odd. Discovering this, you do the computation. I mean, you under this embedding G plus is, for example, mapped to E times B and G minus to F times C. Okay, now you would like to call this duality. So this means you, first of all, this observation is called Kazama-Suzuki duality after the two physicists who discovered this in the 80s. Now you would also like to go in the other way. So now you would also like to have an embedding of SL2 inside super Virasoro times something. So let's think about this. I mean, now here you have your G plus and G minus, and you would like to get E and F out of those of SL2. Well, G plus and G minus have the wrong parity. They are odd, and they have the wrong conformal weight. They have conformal weight 3/2. So what do we have to do? We have to add, again, odd fields, but now of conformal weight minus 1/2. And if you think about it, an odd lattice VOA is always a super VOA. Vectors of odd norm are fermionic, are odd. So in particular, and now the only thing is to get negative conformal weights. one needs the lattice to be negative. So that means if I tensor my super VRSO with the integer lattice VOA, the integer is rescaled by square root of -1, then I can go back. So here, this lattice VOA, let's say, is generated by two fields. And let me use this notation. So let's call this fields x plus -1. They are here the usual lattice VOA vertex operators corresponding to the Heisenberg field y. So, and y having norm -1. And so in particular, what this means is that the OPE of x plus with x minus is equal to, the leading term is already z minus w, and then you get even higher powers, right? On the other hand, it means that the OPE of x plus itself is, what will that be? It will be that will have a that will now have a first order pole. Anyway, but because you glue this with odd fields, this will not be a problem. So here the embedding is given by identifying E with G plus times X plus and F with G minus times X minus. And now it's again an exercise to verify that indeed this gives you a homomorphism of vertex algebras. H then determined by the OPE of the corresponding fields. Okay, now you would like to, of course, phrase this homomorphism a little bit more precisely, so that you not only want to have this homomorphism, but you also would like to characterize it efficiently. And in this case, this is not so hard. So for example, the superconformal algebra is the subalgebra of SL2 times these two free fermions, B and C, and a subalgebra that commutes with a Heisenberg subalgebra. So here, pi alpha is a suitable Heisenberg subalgebra inside this bigger one. You can work it out for yourself which one it must be. And conversely, the same type of statement is also true for the other direction. And by the way, two free fermions, if you bosonize them, then you realize they are the same thing as the integer lattice VOA. So, and if you write it like this, the whole construction becomes even more symmetric, right? Let me give you here one small comment on duality. So the super VRSO algebra is the same thing as the principal W algebra of the Lie superalgebra SL2/1. And here, this level L is related to the level K of SL2 by the formula that K plus the dual Coxeter number of SL2 times L plus the dual Coxeter number of SL2/1 is equal to 1 by this formula. And this formula is a natural analog of the relation that you have for Fagan-Frankel duality, for example, for the self-duality of your VRSO algebra. And I'm not talking about more general dualities, but this is really the first example from an enormous zoo of such dualities, which in particular.
So Thomas, here it's just L plus 1, not plus 2, right?
Plus 1, yeah, because 1.
You use the different.
Yeah, because it's the dual. 1 is the dual Coxeter number of SL2/1, and 2
Oh, okay. I see.
Yeah.
Okay.
So
Yeah. Okay.
it turns out that
Okay.
the level is not the best best number to characterize it. Usually the best number to characterize it is the level shifted by the dual constant. Then it would become more natural.
Okay, thank you very much.
And yeah, you're welcome. So what I wanted to say is, yeah, there's a huge zoo of further such dualities. They're just not the topic of these lectures, but this is enormously interesting. And in particular, Andy, Linshaw, and I, we have done a lot on that. So yeah, topic for another course, what that be? Should be a long one. So now we can phrase this theorem like this, and we can also phrase this a little bit more explicitly, right? What does it mean? Let's see. For example, we can take our SL2 times the free fermions. So we have an action of the super-Virasoro algebra on it and an action of a Heisenberg algebra, and the two commute. So this means, in particular, it's a module for this for these two vertex algebras. And now this means that in particular it decomposes into a direct sum of, in fact, simple modules of these two. So here, these pi alpha are just Fock modules at weight n. The weight is an integer, and this m tilde n. What are these? These are certain super-Virasoro modules. And if I take k to be generic, then these are simple modules, otherwise not. Now, let me now make a comment on the simple quotient. So if I take the lower index, I always mean the simple quotient. And now it turns out the two agree unless I take k to be admissible. But in this admissible case, one has a similar type decomposition, just that now it's not the universal. I mean, it's the simple super-Virasoro algebra that acts. Okay. And now one wants to use this duality to make nice statements of about representation theory, right? It's I mean, you should view this. I mean, these statements tell you that these two vertex algebra are closely related, because you can take one, you tensor it with a suitable lattice VOA, either integer or integers rescaled by square root of -1. And then you take a diagonal Heisenberg coset and you get the other one, and you can go back. Now, the point is you can go back. This means you can define functors. So this procedure tells you in the very first place you can define a functor from the category of modulus of one of them to a category of modulus of the other one. Because you have a construction in both directions, you can go back. Let me tell you a little bit more how these functors are constructed. So first of all, maybe first write a similar statement down for the super-Virasoro for the other direction. So the super-Virasoro times the negative lattice VOA has the same property, meaning it has an action of the affine vertex algebra of SL2 in this case, and that action commutes with the Heisenberg action. So it's a module for this commuting pair of subalgebras. Okay, and now we want to use this to define really good functors between modules of these two. So let me tell you how this goes. So first of all, one defines two new I mean, first of all, let me tell you the general picture. So I take two rank 1 Heisenberg VOAs. I call them A plus and A minus. So this and eventually I want to identify the A plus either with alpha or beta here, and the A minus, it will become clear in a moment what I want to do with those. So, and A plus and A minus are related by that they have opposite norm. So this means the OPE of A plus has some norm, and of A minus has the same norm but opposite sign. So why is this interesting? Because now what you do is you consider a big super VOA called C standing for complex, a complex of vertex algebras, which is just the product of these two Heisenberg VOAs together with a single BC system, again, the same type of free fermions as before. And on this complex, you first of all have a nice odd field, D, which is just one of these fermions times the sum of these Heisenberg fields, right? And because A plus and A minus having opposite norm means that this sum of the Heisenberg fields has norm 0. Right? That's the important thing here. And because this has norm 0, this implies immediately that D has regular OPE. Right? We don't really need the regular OPE, but we need in particular that the 0 mode of D squares to 0. Right? And so this means we can really talk about homology on the super vertex algebra, just the kernel of the Nord module of the image. That will be, whatever it is, it will be, again, a vertex algebra. It turns out this is not quite what you want, but what you want is you want to have a relative complex. So you set the relative complex associated to M, and I'll tell you what M is in a moment. We take this all vectors in the usual complex with the property that they have weight 0 for the diagonal action, for the diagonal Heisenberg action. And we also want that the 0 mode of the other fermion acts as 0. And here by C of M, I mean M times the two free fermions, where M a module for our two Heisenberg algebras. Now, this relative homology has a very nice property. Namely, if I take as my module just a Fock module, a tensor product of two Fock modules, then this homology is almost always 0, except it is a one-dimensional if lambda is equal to minus mu. So yeah.
Here you use d0 squared to 0, right? Not 2.
Yes. Thank you. Yeah, absolutely. Thank you. Yeah, so why is this something nice? Because what can I do now? I can define functors. So now let's define this H for some kind of homology functor. So what you do is you go from one side to the other side. So for example, from SL2 modules to super Virasoro modules. And the minus will then go to the other side. So what do I have to do is I have to start here with a module. So now what do I have here? I can take, if I take this tensor, this with two free fermions, then we have a diagonal action of the super Virasoro algebra. but in fact it's an action of the super algebra times a Heisenberg VUA. And we want to glue, we want to somehow get rid of this Heisenberg VUA. And that's what this homology achieves. Because what do I do now? I tensor this with a Fock module of an additional auxiliary Heisenberg VUA calling alpha minus at some weight. That's where this label lambda comes from. Then I take the corresponding relative complex, right, and then the homology of that. All right. And here I just have to tell you what alpha minus is. What do we need its OPE to be? We need it to be minus the OPE of the diagonal Heisenberg field that commutes with the super-Virasoro action, right? So then what happens? We have this SL2 module n times the free fermion as a direct sum of many Fock modules times super-Virasoro module. We tensor it with this Fock module of for the Heisenberg field alpha minus, and we take a diagonal cohomology. What does it do? This cohomology is the multiplicity of the Fock module at weight minus lambda, which is a super-Virasoro module. And H minus is the same thing, just in the other direction. So we have the same type of thing. We have homology of the relative complex. Now here we again need to add an auxiliary Heisenberg field. We call it now beta minus at weight lambda. We have here our super-Virasoro field. So if we tensor this with our lattice VUA, then we have a diagonal action of SL2 times certain Fock modules for the Heisenberg field beta. And then this homology singles out the multiplicity space of the Fock module at highest weight negative minus lambda. So here. In particular, this homology is 0 if that multiplicity space is 0. So in particular, if you don't choose your label lambda wisely in comparison to the weight support of M, then homology will be 0. But you can always do such a wise choice. So the important thing here is really so you see you have functors that go in both directions, and if you have functors in both directions, then you can compose them, and if you're lucky, they will be isomorphic to the identity functor, and this is true in this case. And I should say, Alyosha Semikhatov has done similar things already a long time ago, 20 years ago, but he didn't use this homological language, which in this case is also not necessary. But if you want to generalize, it's necessary. So if you want to go to more complicated VUAs, you can only do it in this language. This is why I decided to present it in this way. Anyway, these functors, they provide blockwise equivalences of categories. And I didn't tell you here exactly what I mean by blocks, but that has to do with the weight support of the modules, because you can, the functor is non-zero only on a certain block of modules, and then you get these equivalents exactly on these blocks on which it is non-zero. So anyway, I think this is a really neat idea. So what do we learn here? We know from Fagan and Frankel and others that W algebras, they enjoy their self-duality or Fagan-Frankel duality. And now, but this is only for W algebras for the principal nilpotent element. For other W algebras and affine VUAs, the story is much more complicated. And it turns out there is not a dual algebra that is isomorphic, but only if you do an appropriate gluing procedure, which is in this case, this tensoring with a lattice VUA and then taking some cohomology. Now, that's
Hi,
the way
Thomas.
it is.
So I have a question. So is this blockwise equivalence also equivalence as abelian categories?
Yeah, this is in particular as this is abelian categories, and if you have monoidal structure, then it is a twisted tensor equivalence because of the Heisenberg VUA. It's not a tensor equivalence on the nose, but you have some modifications due to the work models.
Okay, that's actually nice. So the result is that the module category for LKS L2 is the same as n equals to super Virasoro module, right? In some sense.
It's a blockwise equivalence. So when it's I mean, they are not the same. They are not equivalent as abelian categories, but
they are not
enough.
equivalent. They are not equivalent as abelian categories.
No, but they have equivalent blocks.
Okay.
So in particular, let me write this as so let me write this a little bit different. This is so we have the classification of weight modules for SL2, and in particular one. So this blockwise equivalence is good enough that you can write down an explicit block decomposition of the super Virasoro category, but I didn't do that because I'm not sure what I would gain from that. But whatever it is, it decomposes as a huge sum of typical blocks plus a small sum of atypical blocks. Right? The only thing one has to figure out is what are here the precise label sets. But and for that one has to look at these functors more explicitly. So you can read it off from our paper, but it's not that you can write it down in 5 minutes. Okay, now now you can see where I want to go, right? What do I want to do is maybe I want to establish tensor category on the super Virasoro side, and then claim that the duality is good enough that you also get it on SL2. So first of all, this duality is good enough in the sense that Jinwei asked whether that's an equivalence of tensor categories, but it's not quite. But in particular, it has the property that if one of them has a tensor category, then you have a tensor functor to the other one. In particular, the other one has a tensor category structure. So, and establishing on super Virasoro is thus enough. But what's the advantage? Every module of super Virasoro is lower bounded. Every finitely generated module of super Virasoro has finite dimensional conformal weight spaces. A module can only be C1 cofinite if these two properties hold. So super Virasoro has a chance that every module is C1 cofinite. And this is indeed true. And now we are in the situation, we know that the super Virasoro has the property that it has a category of modules that is finite length. It's obviously closed under convolution dual, and it's abelian. So this means if we can show that this category is precisely the category of C1 cofinite modules, then we're done. And this is what we can show. So let me do that. And so and the essential, well, yeah, so in the first place, let me maybe extend this equivalence a tiny bit. And this goes back, in fact, to last week. So I will now recall something I already explained last week, which is probably good because it's always good to repeat. Let's first, so now I do somehow a fresh start because I want to do make this correspondence. I want to extend this correspondence. So I first, again, need two Heisenberg VOAs, one of norm k/2, the other one of norm minus k/2. So mu and nu are orthogonal on each other. And then Dragan Adamovich has this VOA that he calls pi naught, which is just a diagonal extension of Fock modules of these two Heisenberg algebras. And why is this such an interesting object? Because you have an embedding of your simple affine vertex algebra of SL2 inside the simple Virasoro algebra at corresponding central charge times this pi naught. Right? This is what I presented last time because it's so useful to construct indecomposable SL2 modules, to construct projective modules. Now I present it because it's again useful. It's again, in fact, very useful. So for example, under this embedding, E gets mapped to the lattice algebra vector E to the C, where C corresponds to the one of the two generators of this isotropic diagonal lattice. The H of SL2 is just mapped to the Heisenberg field mu times 2, and the F has the most complicated form. It's mapped to k plus 2 times the Virasoro field. So only here the Virasoro field comes into the game. Then you get a bilinear of the nu Heisenberg, and you get a derivative of nu. Here this prime is the derivative, and then dressed with the other generator of the isotropic lattice VOA. Okay, and now see, now I have an embedding of SL2 inside something bigger. I know if I tensor SL2 with two free fermions, I have a diagonal action of super Virasoro. So this means if I tensor the bigger thing with two free fermions, I have an embedding of super Virasoro in there. If I take the coset of this SL2 times this free fermion by the Heisenberg, I just get the super Virasoro. So this means if I take the bigger thing times the two free fermions and take the Heisenberg coset, then I have a conformal embedding of the super Virasoro in there. And let me now be more precise with this. So I define a few new fields. X is first of all the diagonal Heisenberg. So I want to take the coset by this the Heisenberg algebra generated by X. And let me also call this bosonize the two fermions. So the bosonization I call Y. Y is then a Heisenberg field of norm 1. And now it's good to introduce two more fields. So first of all, this field C plus Y, and another one W, which is mu minus Y. So then we have that both of them come. What did I? So then this ensures for especially that Z is in the coset, and one second, I think W is not quite right. Oops. Well, let me just go on, but What did I do here? Yeah, double W is not quite right. I have to change this, but let me just go on. So now I take the commutant. I'm sorry for that. So so now I know that the coset of the Heisenberg field of the Heisenberg algebra generated by X inside this bigger algebra is the super Virasoro algebra, and now I want to embed my super Virasoro algebra in something larger. So and this something larger is of course my pi naught times Virasoro times this 2 fermions. So the Virasoro commutes with the Heisenberg anyway, and this pi naught has the property that if you do some computation, let me just write some dots, you see, you observe that then you observe that this one is just isomorphic to another Heisenberg algebra generated by times two free fermions. All right. So in particular, this tells you have, while for SL2 you had an embedding of SL2 inside Virasoro times this funny isotropic half lattice VOA pi naught. In fact, the super Virasoro case is much nicer. It tells you have an embedding of super Virasoro inside Virasoro, 2 free fermions, and a single Heisenberg algebra. That's really, really nice. Okay. So in particular, if one thinks about it, what do you have here? You have a big algebra, Virasoro times this pi naught. You have an embedding of your affine vertex algebra. That's what we want to understand. And then on the other side, we have our pi naught. This half lattice VOA is replaced by 2 free fermions and a Heisenberg. And here you have an embedding, a conformal embedding of the super Virasoro algebra. And now what do we have here? These functors, of course, go also act in the very same way on modules of the bigger algebra. Right? This homology functors. In particular, what you have is and the proof of the blockwise equivalence has nothing to do with SL2 or super Virasoro. It just once it works whenever you have 2 VOAs that are related via this construction. So in particular, what one gets is blockwise equivalences between the following thing. So you have on the top modules for your first big VOA. Let me still call this weight modules. So on the Virasoro, they don't do anything. And downstairs we have blockwise equivalences between weight modules of SL2 and super Virasoro. And then we, of course, and then we have functors in these directions that they just forget. They just forget the action of the bigger algebra and just view it as a module for the smaller algebra, right? And this forgetting is compatible with this H plus H minus with the functors between the categories. So in particular, one has that has also an equivalence between SL2 modules that lie in the bigger structure and super Virasoro modules that lie in their respective bigger structure. Okay. Now, why is this important? Because now, first of all, I need now one explicit result by Adamovich. It says that let M be a simple. So it's a statement that this free field realization, or this pi naught times VRSO realization, is very good in the following sense, that let M be a simple module for SL2. Then there exists an M tilde in the bigger algebra with a property that which surjects on M. So this means every simple module of SL2 appears as a quotient of a module of the bigger algebra. And as a corollary, the same holds for super-VRSO. I can copy paste. With the same property. Okay. Now, okay, so this is the first ingredient one needs in the, and this corollary is the first thing one needs for the proof of C1 cofiniteness. And now the second one is it's best now best things are best phrased in terms of formulated in terms of least filtration, something that is well known. And so let me just set it up in this in this setting here. So least filtration. So we have a VOA. We don't want it to be integer graded. Half integer graded is good enough. So Lee only formulated it for integer graded, but you can go over it. That's not important. And we want this VOA to be finitely strongly generated. So x1 up to xn is a set of strong generators, and we want them to be homogeneous. So they have conformal weight, which I call delta 1 up to delta n. So then the VOA strongly generated means that the VOA is spanned by words in the negative modes of these strong generators. Acting on the vacuum. And now one defines subspaces Fp of V to be the subspace spanned by words that are not too long. Meaning here that the conformal weight of the fields adds up to at most P. Right? And notice that the mode index, this minus n1, is completely irrelevant for this one. And similarly, you can also define such subspaces for a lower bounded module. So that is which is generated by a top level. Then we can define this completely an analogy. Any words, any monomial acting on a top level vector. So that also gives us a subspace of our module. And usually what you do is you use this to get a filtration. So you write a clearly fp minus 1 is a subspace of fp. So you can take the quotient, and then that gives you the associated gradient of your VOA. I really need the this filtration to prove C1 cofiniteness. So what do we have here in our case? We have a big VOA, namely our Virasoro algebra times the Heisenberg algebra times the two-free fermion. And so this one is strongly generated by the Virasoro field, which I call L, the two fermions, and the Heisenberg field, which I denote a W, and the corresponding filtration I denote by an F. And the conformal weight of the Heisenberg field is 2. The fermions one gives conformal weight 1/2, and the Heisenberg field 1. And on the other hand, super Virasoro sits inside this algebra and is strongly generated by its Heisenberg, its Virasoro field. It's not the same as the Virasoro of the Virasoro in here. The two odd fields and another Heisenberg field. And here the conformal weights are 2, and for this one 1. And now, in order to make these two filtrations compatible, one gives the G plus 5 conformal weight 5/2. Now the G minus conformal weight 5/2, and the G plus conformal weight 1/2. So here, now what do we have here? Here we have something, so filtrations you can define on a module, but now here we are dealing with modules that are modules for the big algebra and for the small algebra. So this means we have filtration as a module for the big algebra and as a module for the small algebra. Now, what do we have here? The filtered spaces for the big algebra are bigger. So you can, if you think about it carefully, you see this. So when one has this inclusion, it's by construction, this is true. Now, the point is, by carefully comparing filtrations together with knowledge about the Virasoro algebra, so nothing is better known than the Virasoro algebra, well, maybe, one can then prove C1 cofiniteness. And let me state the theorem. Let me now state the theorem, state a few corollaries, and then give a sketch of the proof. So let M be a Verma module for the Virasoro algebra at this central charge, CK. Let L be its simple quotient. Let K be not an integer, not a positive integer. Then the following statement is true. This module L is C1 cofinite as a module for the Virasoro algebra. This is equivalent to the module L times the fermions times an arbitrary Fock module is C1 cofinite as a module for the super Virasoro algebra. for all weight labels. This looks a little bit funny anyway. That's the theorem. So in particular, C1 cofiniteness of Virasoro is completely known. So this means this theorem gives you C1 cofiniteness of modules that you can realize via this Adam-Wedge trick. I'm quite confident, but I haven't thought about this in more detail, that this theorem implies, in fact, that a super Virasoro module is C1 cofinite. A highest weight module of super Virasoro is C1 cofinite if and only if it is not a Verma module. That should be true. That's maybe a conjecture here. A very interesting one. So a corollary is that the super Virasoro category with a lower index, this for the simple super Virasoro, because if for the simple Virasoro, super Virasoro, no Virasoro module appearing there is, every Virasoro module appearing there is C1 cofinite. So this means this theorem applies to every module appearing in that realization. Anyway, the corollary is that this category is C1 cofinite for admissible level. And this corollary follows immediately from the previous corollary, this one here, together with a theorem of Huang that a homomorphic image of a C1 cofinite module is always C1 cofinite. So this is why, together with a homomorphic image of a C1 cofinite module being always C1 cofinite, and together with the statement that if you have a category in which every simple module is C1 cofinite, then already every module of finite length is C1 cofinite. So this is a direct consequence, and then one gets the desired consequence, namely that the category of super Virasoro weight modules is a vertex tensor category. Well, the C1 cofiniteness was the only thing that was missing in order to get the vertex tensor category. It's the complete category of C1 cofinite modules. So this means that closure on the tensor product follows immediately. Well, and so one gets the tensor category. And then via this duality, one gets the very same result for SL2. And so now you see a huge detour, but we unfortunately, this is maybe the nature of the whole theory, is we are interested in SL2 at admissible level. It has these modules that are not lower bounded, so there is no good criterion for existence of vertex tensor category. So what do? We look for a duality to some other super VUA that has many more lower bounded modules. We prove C1 cofiniteness there, and so that we get the vertex tensor category there, and then we hope that the duality is good enough, and we can prove it, that it also establishes the tensor category structure on the other side. And this is all, in this case, indeed true. So I think this corollary is a very important theorem, because this is what one really wants, right? One wants to have tensor category, and now we got it finally for one example of an affine vertex algebra with all these lower bounded issues, etc. Okay.
Here your K does not include positive integers, right?
No, but for those we know it anyway.
Yeah.
Yeah.
So can you say, so what precisely is this C1 cofinite statement you have? I mean, it seems like what you're saying is that you show that simple modules are C1 cofinite.
Yes, so the C1 cofinite statement goes in 2 steps. It shows every module of the bigger algebra is C1 cofinite as a super Virasoro module, but then but that implies, because every simple super Virasoro module appears as a homomorphic image of a module of this bigger algebra, it means that every simple module of the super Virasoro algebra is C1 cofinite, but then every module of the category is C1 cofinite. That's a theorem.
And how are you defining this category exactly? It's
how I define this.
You say weight module.
Yeah, so it's the category of it's really just the category of modules for the super Virasoro algebra that have the weight condition, and they are modules for the simple super Virasoro algebra.
Okay.
I don't.
Is there some assumption about finitely generated or something like that?
Yeah, infinitely generated. Yes. Finitely generated weight modules for the super Virasoro. Weight just meaning semi-simple action of the Cartan subalgebra.
Okay.
Just because this correspondence goes of it maps finitely generated to finitely generated.
Okay.
Any further questions?
So how did you use least filtration? So you need a finite generated plus least filtration stuff to prove C1, right?
Yeah, exactly. So I mean now I did I presented the outcome, and now the question is how does so this is an important theorem. So it's I would say it's at least important that I sketched the proof idea. It is in fact nothing but a long computation. So let's see. We take M, a module that is not simple. And now here yeah, I should be so we take here a module M of this one. This is a little bit more clear. We take M to be a Virasoro module times the 2 phi fermions times a Fock module. So and now I'm sorry. I take a Virasoro module times the fermions times the Fock module, and now if this is not simple, this module is not simple, then it has a singular vector, and of course this must be a singular vector for Virasoro, because the other ones are right. Fock module is always simple, and the free fermions is just the simple VOA. And so let's call this singular vector S. And one knows how the singular vectors of the Virasoro algebra look like. They are of the form S is equal to Virasoro minus 1 to some power acting on the top level vector. So this is the top level vector. Plus additional stuff. So here M is a highest weight module generated by a top level vector. And now one has to think about can we characterize the singular vector with respect to our filtration? And if one thinks about the details, well, this vector is in F in the filtration F of degree 2n, but not of 2n minus 1. So this means in this quotient, it is in there, and we also know what's its conformal weight. Well, its conformal weight is n, and its Heisenberg weight is it's a Heisenberg weight. Let me denote by mu is just the weight of the top level here, lambda. And so anyway, this quotient, if one thinks about it, is one-dimensional and simply spanned by this leading term. Right? But now what do we have here? We know our other filtration, the filtration that describes super Virasoro, I mean, we have the GP is inside an FP. So in particular, if I don't quotient by F to n minus 1, but just by G to n minus 1, I get something larger, right? But whatever this larger thing is, on my L minus 1 to the n is still in there. So this means the lemma one has to prove is, which is nothing but a combinatorial statement, is that our m modulo G to n minus 1 m at this conformal weight and at this Heisenberg weight is spanned by 3 vectors. Namely, the Heisenberg field of the super Virasoro acting on the top level vector, I mean the minus 1 mode. Then you can have this expression. When one just does the combinatorics, right? A conformal weight has to be high enough, but also a filtration degree has to be high enough. And then it turns out there are only 3 possibilities for that. So now, if we think about the C1 condition, well, this x minus 1 tells us that this vector here is already in the C1 subspace, but the other 2 are not. So, but what it tells us is that what it tells us, anything in this G2n minus 1 is already in the C1 subspace. So what it tells us is that our singular vector can be written as a linear combination of these 3 plus something in the C1 subspace. And now one has to analyze whether the coefficients of these 2 terms can be non-zero. And for that, one uses the commutation relations of the super Virasoro explicitly. And it turns out generically these coefficients cannot be 0, which gives relative quickly the C1 cofiniteness generically. So let me write this down as a corollary. So for as long as conformal weight and Heisenberg weight are not badly chosen, meaning here we have these 2 not allowed values, then one can show that that these 3 vectors are already in the C1 subspace of the simple quotient. So here by M I denote the image in the simple quotient of M. In other words, this simple quotient needs to be C1 cofinite. And then and then in order to get also these bad labels, one uses Miyamoto's theorem if one has an intertwining operator of 2 simples. to something else, then the image must be C1 cofinite as well. But using this nice realization that we have, it's easy to find the intertwining operators. So, yeah, I think I was a little bit confusing at the end. So let me first write down the theorem. The theorem follows, since one has this very nice statement that if one has an intertwining operator of type Mn to R, that is surjective, and M and N are both C1 cofinite, then also R is C1 cofinite, and it is easy to find good intertwining operators. Okay, so the idea of the proof is you have this embedding. This embedding tells you in particular, and it's embedding inside something with Virasoro. Virasoro is well known. So in particular, you know the leading form of singular vectors. But that helps you because it tells you that it tells you whatever the singular vector is, it must be modulo C1, a linear combination of 3 vectors, one of them not being good. So this one here is not good because it's already in the C1 subspace. But the other ones you need relations for those. And so so then it's a matter of playing around with commutation relations of super Virasoro with its action to see that generically that's this corollary. These 2 vectors must appear with non-zero coefficient. But once they appear with non-zero coefficient in the singular vector, then C1 cofiniteness follows essentially immediately. And yeah, and that's how you get it. Okay, so yeah, I think this was a little bit technical at the end. So the important thing is one now has the tensor category on SL2, and the trick was you need to have C1 cofiniteness to establish tensor category. You can't do that for SL2, so you do it for super Virasoro, because there you have a chance. And the way you do it then eventually is simply by a tricky computation. Yeah, let me stop here for today.
Okay, let's thank Thomas for today's talk. Thank you.
Thank you, Thomas.
Yeah, you're welcome. So I hope that I will present tomorrow a trick to compute some fusion rules, and well, and then I have exhausted what I can tell you on new things. Yeah, I'm writing these things up at the moment, so it's all very new, and yeah. So
I have a question.
Very nice talk.
Oh, sorry.
Yeah.
One
Please.
question. Doesn't this show that the irreducibles are not Fermat's? The thing that the C1 cofinite irreducibles
are not
Fermat's?
Yes. So what the only thing that is missing is so here in the theorem I'm dealing with Verma modules for Virasoro. So what do you have to show is you have to show that every Verma module of super Virasoro can be realized via Trajan's construction.
I see. Thanks.
This is definitely. And how do you show this? Well, you do this construction, you simply list everything you can do, right? And every module that you construct is, I mean, you do this for the universal VOA, then it's just by looking at the character, you see that it's a Verma module. and moreover, it's uniquely determined by conformal weight and weight. And you just have to make sure that you can get all of those, which is a computation. Surely the answer will be yes. And then you're done. So I just didn't. So I'm sure that this is a very easy, very simple consequence of my theorem here. And this is very interesting because this means we should also be able to get tensor category for generic levels here, right? The only thing that is missing for that is to show that to show finite length supervior solver, right? Which I haven't thought about yet. Yeah. But I would like to discuss this with you.
Can I ask a question?
Yeah, please.
Is there a relation between taking a homology of relative complex and taking a commutant?
Yeah. In general, you have a very nice. So in general, if you have a big VOA V that has an affine subalgebra, let me write this down for universal ones. So now, so then you want to understand what's the commutant, and what can you do is you can take V, you tensor it with the affine VOA that you're interested in, but not at level k, but at level minus k minus twice the dual Coxeter number. So then, and then you can look at this at the relative complex on this. This has now has a diagonal action at level minus 2h check, which is the good one to have a standard Lie algebra differential for, and then you can take the homology to this. And for generic level, these two are isomorphic. So this holds for generic K. And it's quite useful.
Thank you very much.
Okay, you're welcome. But I have to assume that V is, no, I don't. Yeah, I think, yeah, no, but yeah, exactly, this holds.
Okay, are there any more questions? Okay, if not, let's thank Thomas again and see you tomorrow.
Yeah, see you tomorrow.
Come on,
everyone.
see you tomorrow.